Yeah, in this third example, I decrease the step depth to a factor of 2. Then in theory, I get a Kc value, which is 2 times this, that is 11.8. The T max value is half of this, half of 7. Where is it? 7.4. It is 3.7 seconds. Now you are theoretically has a double speed, and the peak is Kc times step depth, which is 23.6. As you see, that is a limitation, but not so large than the limitation of 590 volt. So here, of course, you are at the limitation, and the question is, how large is a negative nonlinear effect? See simulation with Rexy Sharp. So we go back to this program. Now we change the parameters here to 11.8, step depth 2, and say OK. And first I want to show you without limitation, large value here. So theoretical curve comes now. I want to store this curve and recalculate now what happens with step depth 2. You see, theoretically not so fast than step depth 10. Double speed. Yeah, this is 7.6. That is 3.4. Overshoot is okay. This is the theoretical temperature curve. And finally, I want to have the situation if we have a limitation. I want to have 22 volts. I get only 10 volts. What happens now with this curve? You see now with the orange color. Okay, of course, slower, but the overshoot increase is, I think, acceptable. The situation we can do now in real life is we select step depth 2 and then decrease Kc as long as this overshoot fits within my tolerance range. That is the way we can do this in real life controller design. But I think this is then the final result in the workbook on page 25, I think. Let's have a quick look on the table, resulting table. I have added here for line 4 and 5. You see Kc is 11.8. Double speed than this, theoretically 2.5%. Here I have measured 7%. Okay, 6 seconds, TM. Let's look. This is no 6 seconds. The overshoot, that's okay. But 7%, I think in that paper I have really less than 7%. This is just, let's show this curve. We go with the cursor to the peak here and say this is 4%, yeah, 4%, not 7%. No idea why I have got this type of values. Okay, I think now the next step is I show you measurements. Yeah, in the workbook I have seen that there is a small difference to that what I have done here. The difference is very simple. In these curves I start at 0 and goes to 1.5. So I make a much larger, 50% larger step amplitude and gets of course then larger overshoots. Next is we have here the AWU information, that is the anti-wind-up mechanism. This is an internal procedure, an internal software change in our PID controller, which helps to avoid wind-up overshoots. I just show what happens in our situation. I go to the controller, activate here this anti-wind-up function, say OK, and repeat the calculation. Here of the orange situation, I've stored this curve, and the next color is light green. If I recalculate this, you see with steps 2 and anti-wind-up function activated, we get now no overshoot, fast reaching the final value, faster than a PI. So in reality, if you are able to realize anti-wind-up in software, digital controllers, it is easy, but in hardware digital controllers, in hardware analog controllers, it is not so easy. So then you have to live with the orange curve. But if you can realize anti-wind-up functions, then you can remove these nonlinear overshoot effects of wind-up mechanism. Yeah. Now we have a quick look on the realization of the controller. With the parameters 10 second and KC is 5.9, steps 1, the PI controller has no R3C1, has only an R2, C2 and an R1. I selected this circuit. These are the copy of my relation between the T's and the R's and C's. And I selected an R1, which is 220 kilo ohm, a C2 of 7.7 microfarad, and this leads then to an R2 of 1300 kilo ohm or 1.3 mega ohm. And then I select the steps 2 version with KC is 11.8. This results then in the same C2 value, but R2 is different. No, C2 R2 is the same, but only C1 is added with 4.5 microfarads and R3 is added with 110 kilo ohm. R1 is also unchanged. No, R1 is 110 kilo ohms. So what I have selected here is unchanged R2C2 in both cases. So this is changed from PI to PIDT1 with these values, and R2C2 is unchanged in both cases. It is the same. Then I show you now the resulting measurements with my real hardware. I have connected the PC. With the PC I can store the measured values, and here you see the result. Note that the step goes from 3.5 to 5 volt. So here I have done not a 1 volt step, but a 1.5 volt step. That's some years ago I have done this. And note that now the overshoots are just much higher than expected. So sometimes, if your theory with your simulation gives good results, and then you go to your hardware, and then you have changed results. The question is, what is the reason for this difference? I tell you the reason. There are two main reasons that we have differences to my simulation. The first reason is the actuator is non-linear. The actuator has a curve. I make a small note for this. Differences to measurement against theory. First is a nonlinear actuator. We have assumed a linear actuator, but we have measured it non-linear actuator. The actuator we use triacs. Triac, maybe you have heard it. Triac is a semiconductor hardware which can do the following, which if you have an AC voltage, a triac can switch on the voltage to a later moment than a zero crossing. So the triac switch on maybe the sinusoidal signal here, but can't switch off, only switches off at the next zero crossing. So a triac gives this signal to the actuator. This is the current caused by triac, after triac. And this delay time is proportional to UP. And you can imagine that the power under this curve is proportional to the power, and if this is a linear relation UP with this T, the power is nonlinear, and we have measured the curve power over UP, and this looks like this. This was my 1700 watt, and this was my 10 volt. This point is okay, this point is okay. We assume a linear connection. We have calculated our simulation, and our calculation assumes a linear curve, but caused by this mechanism we get this type of curve, a real nonlinear curve. So for small UP values we have nearly no power, and for large UP values, we reach approximately the linear part, but this caused a strange behavior in our measurement. That's the first idea. And the second, what we have done in our science, our investigations with this system. Second, the process model is too much simplified. Process model is too simple. With another identification method, with more accurate measurement, identification, we get a model which is consisting of 3 PT1 and a delay. And if we designed the controller with this more sophisticated model, then we get better fit between theory and measurement. Different controller. So sometimes it is necessary to work with nonlinearities, and sometimes it is necessary to make a better model, and then the theory and the measurement fits better together. So the resulting measurement is a little bit a pity that this doesn't fit so good to our hardware. The theory and hardware doesn't match. But I can show you in our lab we have also the same situation, a PID controller with a 2PT1 model, but then this is a speed control system with a DC motor and a tachometer, and then without this non-linearity, without this difference between theory model and real model, we get much better coincidence between theory and measurement. So wait for the lab measurement of our speed control system, then this fits much better together. Okay, so far this is the closing of my chapter 3.8 temperature control system.